So the original problem that I was trying to explore was how much do carbon emissions need to be reduced in order to stop or at least slow global warming to an acceptable rate, at least a rate at which humanity can survive for an extended period of time. And so what I did was I did a little bit of research into this problem and I created a Stella model in order to explore this program. My name is Marcus Robinson and this is the presentation that I have prepared. So this is the main problem is that carbon emissions are rising. Right now we're at about 380 parts per million in the atmosphere. And this rate is above acceptable levels. In order for the Earth to roughly maintain equilibrium, we need to be somewhere near 350. The longest that we can live for over a century is probably at about 450 parts per million. Now, at the rate that we're growing right now, the amount of carbon entering the atmosphere is fluctuating between 1.8 and 2.2 parts per million per year, which means that if we continue at just this rate, we would reach unacceptable levels in just over 100 years, just under 100 years. And that's really going to be a serious problem. But the other problem is that the rate at which carbon is entering the atmosphere is actually rising and becoming higher. It's estimated by the 2050, the amount that carbon will be entering the atmosphere will be nearer to 3 or 4 parts per million, and that number continues to get worse, both as humans consume more and more carbon energy, but as the planet is unable to remove that carbon dioxide from the atmosphere. Now the problem with this is that as high temperatures get higher and higher, we witness a huge host of problems. And this includes changes in weather patterns, increased droughts, melting ice caps, and mass extinctions of species as weather patterns change, and the problem becomes worse and worse. And so that's going to be a serious concern. And so we're going to have to explore what humans need to do in order to solve this problem. So these are the rough behavior over time graphs, how the basic stocks in this model are going to perform over time. And there are 3 important ones. First of all, we see the first one in the upper left-hand corner is the CO2 levels in the atmosphere over time. Now this is if we change nothing within our energy policy. Those carbon over time are going to continue to grow exponentially. And the same behavior is true for the overall temperature of the planet. It's going to react as carbon dioxide levels increase. Now the bottom graph, what we see, is human consumption of energy based on and the amount of that energy consumption that comes from carbon sources. So right now we're at about 85% come from carbon sources. It's estimated that about 67.5 is going to come from carbon sources by 2050, and then finally by 2100 what we're going to see is that about 25% of our energy comes from carbon sources. That's the rough estimate if we continue how we're going right now. But what we still see is that the behavior over time still exists for these other graphs. So that's what we want to explore in this model. So the first thing that we did was started by building the model. And this was the first model that I built on this problem. And it's really simple. What we see is that the higher stock value shows, the stock value up there, shows that is the level of CO2 in the atmosphere. And the stock value below it is the temperature change over time. And there's just a real rough relationship between these two things. Essentially, as CO2 in the atmosphere rises, the planet warms. And as the planet warms, the ability of the Earth to remove CO2 from the atmosphere and the amount of CO2 that the Earth puts into the atmosphere increases and decreases respectively. And so the Earth moves farther and farther out of equilibrium at a quicker and quicker rate. But this didn't really explore the full problem. And in fact, the relationship between CO2 and the global temperature difference is actually different. So I recreated the model in this form. And the difference in this model is that instead of the planet rising over time as a result of parts per million in the atmosphere, there's actually a maximum amount that the planet can rise based on the level of parts per million in the atmosphere. It's estimated that for every 100 part per million that enters into the atmosphere, the planet's going to rise between 1 and 1.1 degrees Celsius. And this new model reflects that, as well as continuing to have the feedback loop. The final element that I wanted to add into this model, in order to explore the real problem, is how humans are having an impact upon the atmosphere. And so I'm adding in a third part of the model, which is going to be shown later when I show the final model, but the idea of the amount that humans are putting into the atmosphere, and that's going to be added in. But we're going to focus on the important parts of the model first, the various aspects that are really affecting the feedback loops and the relationships and behavior that we see within Stella. So the first part of the model is the upper half of the model, and it's the same as what we've already seen. It's how, as the global temperature difference increases, that's the ghost stock on top, increases, we see that the planet warms more because more energy is being released as as the ocean warms up, it's less able to take carbon dioxide out of the atmosphere, and as the planet warms up, more and more trees are becoming susceptible to things like forest fires and are being cut down. And so as a result of that, the planet more carbon dioxide is entering the planet. And so we have this relationship, and that's the top half of the model. The next important aspect of the model is the impact that CO2 has on the rate at which the temperature increases. And I already explained that a little bit, but as CO2 increases in the atmosphere, the rate at which the planet warms increases. Now, there's also another important feature, which is this idea of the delay feature, and that's right there. And the delay feature is that the planet doesn't warm immediately as a result of parts per million. Sometimes there's long, extended feedback loops. Essentially what happens is as the planet warms, it slowly warms the ocean, and that takes some time in order for that to happen. Another thing is that the polar ice caps melting, and that affects the time. So we see this long duration of a feedback loop before the temperature of the planet really catches up to the amount of carbon dioxide within the atmosphere. So that slows the rate at which the planet is warming, but we still see that eventually it's going to reach that target planet temperature, which is about 100 parts per million for every 1 degree for every increase of 100 parts per million. And that's going to really affect the temperature of the planet the most. The final part of the model that we have is this added element of how humans impact the planet. So there's really two distinct portions, and we'll start with the top half of it, which is going to be our stock value, which we see right there, and how that affects CO2 within the atmosphere. Essentially, the basic behavior that this model exhibits is the idea that humans are going to be consuming more and more energy over time, and less of that energy is going to be coming from carbon sources. And then we're able to explore and play around with what rate needs to be done in order for the planet to reach equilibrium. So that's exhibited in the top half of the model. Another interesting element is that as global warming becomes more and more of a threat, it impacts the way that we generate energy policy. And so we have the bottom half of the model right here, which really modifies the rate at which we're having energy come from other sources. Essentially, if we look back to about 50 years ago, no one had really heard about global warming, or if they had, it was in small elements. But as the situation becomes worse and worse, and the problem becomes worse and worse because the planet has warmed more and more, and we're experiencing these other symptoms, energy policy changes, and that energy policy change means that the amount of carbon that we're using is going to be shifted as a result of this. And so it's important to notice the relationship that this causes versus the relationship that the other half of the model that we've already seen causes, and that has some interesting results. So this is the overall final model with all of those important pieces put together. Everything kind of works together, and it exhibits some good relationships. So this is the first feedback loop that we have. This feedback loop is probably the biggest feedback loop within this model, and it's how humans are impacting the levels of CO2, how CO2 in turn affects the temperature of the planet, how the temperature of the planet then in turn affects our energy policies, which affects our energy consumption in percent carbon. So a green relationship shows that there is a positive feedback loop between those two things. So as one of them increases, the other one increases in turn. Now the red is a counteracting feedback relationship, which means as that increases, the following value decreases, or if that one decreases, the other one increases. So we have this counteracting. Overall, this part of the model is going to be counteracting because there is only one red portion of this model. So as CO2 rises, that means that the global temperature through the relationship actually ends up increasing. And as that temperature increases, what we see is that energy policy is adversely affected. We're more likely to reduce the amount of our energy that comes from carbon. So that number goes down. And that affects our energy percent of carbon. Now, as there's less and less of our energy coming from carbon, there's going to be less and less CO2. So we have this counteracting relationship throughout the entire model. And it's important to contrast this feedback loop with the other feedback loop of the amount of carbon dioxide that we're putting in the atmosphere. So the real question within this model is this feedback loop fast enough to counteract the amount of damage that we're doing to the planet? And this leads us to what policy changes need to be implemented in order for us to see some progress. So the first thing that we need to do is we really need to reduce the amount of our energy that comes from non-carbon fuels. The other thing we need to do is reduce the overall amount of consumption that we have, but we're going to focus on this policy. One of the important things is that policy has to be quick and it has to be dramatic. And if we don't have a quick and dramatic policy, then it's simply going to be too late because the Earth will have already been knocked out of its pretty precarious equilibrium. So this leads us to the results of kind of what this model has done. So the top graph that we have is essentially what we're impacting. What we're impacting is this idea of the rate at which our energy consumption changes. So what we see is that number 2, that red line right there, is the baseline, and it shows the relationship as predicted right now in terms of the amount of energy consumption. So that's the baseline that we're working with. And as you see, the result of that is, again, the number 2 line in terms of the global temperature difference. It means that the planet's going to raise by about 4.5 degrees, and we're going to be at unacceptable levels. So what we did is we experimented by doubling, tripling, and quadrupling our energy policy and seeing what impacts that would have. So those lines are 3, 4, and 5 respectively. So what we see is that for 3, the planet still warms to about 3.06 degrees. And that's still an unacceptable level, and it's not really showing signs of being able to completely level off because the equilibrium has been completely ruined. However, for 4 and 5, we actually see that the planet is able to reach equilibrium and slowly begin cooling by the end. However, those temperatures are still going to have dramatic impacts on the Earth. 5 is actually the only one in which we're going to be able to live on this planet without super dramatic changes. Obviously, we're going to be still experiencing droughts, species extinctions, and other problems like that. But it's not going to be as dramatic. And the only way that we're going to be able to reach this idea is if we quadruple our energy rate. It means that by the year about 2067, we need to have reduced all of our carbon emissions down to 0. And then the Earth is going to be in a state where it has to be able to maintain its own equilibrium. And that's going to be really difficult for us to do, because what we're seeing within this model is because humans have so much reliance upon carbon energy. So this is a really frightening model in terms of the Earth being able to continue living in the way that it is. So what have we learned? First of all, the Earth has a really precarious equilibrium. It's this idea that the Earth is able to maintain balance, to maintain a stable set of CO2 levels. But if we unbalance that by adding more CO2 from humans, that equilibrium is ruined, and it can make it impossible for us to reestablish an equilibrium quickly. So the result of this is that we need a quick and dramatic energy policy. If it isn't quick enough, if we don't reach this 0 carbon percent level by a certain year, then we're going to be experiencing all of these problems. Finally, the really important thing is that modeling is going to provide us with a really superior understanding of this problem than any sort of other discussion or lecture that we could listen to. Because essentially, by building this model, I was able to interact with the pieces of the model and make it into something a little bit more dynamic, a little bit more breathing, something that was really real to me. And that's a lot different than listening to something or reading a paper on it. And so what we see is that, first of all, this model is providing us with some answers about what needs to be done about all energy policy, but it also really gives an interesting way of examining the problem in a different perspective. So thank you for your time.